students like this has ever produced, if not the best. So we'll talk about something very interesting on permutation patterns. It's the last talk of the seminar, and we're going to take Vince and his girlfriend and the young girlfriend to dinner at the usual place. But if you'd like to join us, please let me know, and we'll have talk. I'll be standing here taking names. So everybody is welcome to join us. Thank you.
Thank you, Darren. So, let's talk about permutations and containment, and I'm going to start at the very beginning. So, first of all, this is joint work with Michael Albert in New Zealand, Shane Hamburger, and Jay Pentone.
That chalk is essentially invisible. Right, press hard.
Okay, I'll try.
I think where you're sitting.
I think it's the
No, your angle.
The
No,
glare.
Oh, I think it's the angle. Oh, I see.
So, I'll try harder. Shane Hamburger and Jay Pentone, who were graduate students at the University of Florida. Nathaniel Starr, who was a graduate student here at Rutgers under Daron and myself. So just to go way back, in The Art of Computer Programming, Volume 1, it's often said that he characterized the permutations that can be sorted with a stack, but actually the way he wrote it was the permutations that can be generated with a stack. So the way this works is that we have what's called a stack here. And to generate a permutation, we think about feeding the stack some numbers in increasing order. And what they get to do is they get to go onto the stack, so we can push. So we can push the 1, and then we could say push the 2, and then we could maybe push the 3, and they can also come off the stack, which is a pop. So now we could say pop the 3, push the 4, pop it, pop the 2, and then let's say push the 5 onto the stack and pop it, and then finally pop the 1. So this shows that 3, 4, 2, 5, 1 can be generated with a stack. So a stack is just a first in, last out data structure. And we're interested in generating things with these data structures. So Knuth's result was that pi can be generated with a stack if and only if it avoids 3, 1, 2. Okay, so I should just explain this word avoids quickly. I'm going to think about permutations as their plots. So a certain permutation, I might just draw it as, let's say it's 3, 1, 4, 2, 5. I put a dot at the point 1, 3, 2, 1, 3, 4, 4, 2, and 5, 5. And containing, well, avoiding 3, 1, 2 means not containing 3, 1, 2, and containing 3, 1, 2 means we can find 3 points that look like 3, 1, 2. Okay? It didn't have to be exactly 3, 1, 2. Sorry. This could have been a 4, 1, 2, or a 5, 1, 2, or a 5, 2, 4. They would all be copies of 3, 1, 2. Okay, so this is Knuth's result that really created this whole field of permutation patterns. And later, I believe this was in actually The Art of Computer Programming, Volume 3, he studied another data structure, which are queues. So 2 queues. So one queue is a very silly data structure. A queue is just a first in, first out structure. So one queue is silly because if we put the if we start with 1, 2, 3, 4, 5 in that order, if we only had one queue, we just put them into the queue and put them out. But if we have two queues in parallel, now suddenly we can do something. We can choose which of the two queues to put the elements in. So what I'm really doing, and if you think about it, it doesn't, we can just fill up the queues and then we can do the output as we like. It's not going to matter. So we can just take some increasing subsequence here, put it on the top queue, take the rest, which will be another increasing subsequence, and put it on the bottom queue, and then choose among those which to output when. And we can do this in such a way that, well, we can do this in any way we want, so we can get anything that's the union of two increasing subsequences. So this can sort, so two queues in parallel can generate anything that's the union of two increasing subsequences, and that's equivalent to avoiding 3, 2, 1. This can generate pi, if and only if pi avoids 3, 2, 1. And this inspired, these two results inspired a ton of work. There's a lot of different things you can think about. You can say take two stacks in parallel, and we don't really have a nice answer for that yet, although Michael Albert and Mireille Bousquet-Malou have the best answer so far. You could modify the queue. You could say you could add to kind of the front or the back. We don't really have a good answer for that. You could form a much more complicated network where you can go maybe through a stack and then through two queues in parallel. Or maybe you could do two queues in parallel with a stack. There's lots of things you can do, and that was all the early work, was networks of sorting machines. But then, and this was really, all this work was inspired by a question that Henning Olfersen asked us back in 2012. He said, are there any new sorting machines? Okay. And really we were thinking about it, and there haven't been any new sorting machines in a very long time. We had stacks, we had queues, we had these double-ended queues, which are called deques. And then, there are other things that people have called like forklifts, and we could restrict the size of the stack. There's other modifications, but they all look like this. And so we started thinking, how could we create a new sorting machine? And so this is what we came up with, was the notion of, well, generating permutations with, so we're going to generate permutations with a restricted container. So this restricted container is what's going to take the role of the stack or the queue. So the picture for these is going to be an input, which is increasing, that somehow feeds into some box, which is the restricted container, and then that somehow leads to the output. Okay. Now, let's give you the rules.
So do you want to generalize all these?
Yes, we want to generalize stacks and queues. And I guess transit deck queues, but mostly stacks and queues. Okay, so here are the rules. This container, well, in the AVB machine, so I'll explain this in a second. For every set B of patterns, so these are things we might avoid, like 321 or 312, we're going to have an AVB machine. The rule is that the container has to always avoid those patterns. Okay, so we're not allowed to have any elements in here that look like one of those patterns. And then we're allowed 3 operations. The first 2 are exactly like for a stack or for a queue. We can push the next entry from the input. Okay, so we're going to push it into the container. But, well, with a stack, we made a rule kind of that it has to go on top. With the queues, we made a rule that you have to pick which queue you were putting into, and it had to go in the back. Here we're going to make the rule that the container holds a subpermutation, and you can push this next entry into the container anywhere you want, so long as it's what's in the container still avoids B. So that's the key thing. Anywhere, so that the container still avoids all of B. Second thing, you can take something out of the container, but when you take out of the container, you have to take the leftmost entry. So you can pop the leftmost element of the container.
So the container's ordered.
Yes, sorry, the container is ordered. And when you insert something, you're allowed to put it anywhere you want, as long as it's still ordered.
Linearly ordered. Yeah.
What's that?
It's a linear.
Yes. Yeah, sorry, it's a subpermutation.
But you can insert it anywhere you want?
Yes.
But the
Sure.
box is misleading. That's the one-dimensional box.
This is a 2-dimensional box.
But,
Oh, what's in there?
yeah.
Well, I'm going to think about it as being a subpermutation, so
Okay. Oh, right.
that might look like that.
Okay.
But yeah, when you go in, really this arrow might look like many possible places to put it, only one place to pull it from.
We
As
can
long as
think,
it avoids B.
we can think of it as a register.
Yes.
Yeah, yeah.
So we can pop the leftmost entry of the container. Well, into the output. And again, it has to go to the end of the output. We're just outputting elements of the permutation in some order. And then I'm going to make a rule that might seem a little bit odd. We do it for a theorem that's coming up. So I'm going to allow a 3rd operation. Bypass the container. Okay. Which what I mean is just take the next input symbol and put it on the end of the output. The next element of input. Yeah. So I should go over here and correct this figure a little bit. Really, the push arrow should look more like that. We're pushing anywhere so long as we avoid B. And then there's also a bypass where we can just get it out. Okay. The reason we allow bypass is, again, for a theorem that's coming up, but it turned out in all of our examples we were allowing ourselves to put an entry there so we could just push and then pop out. And it's just cleaner to allow bypass as an option. Okay. So if we go back to the stack, let's think about the stack in this set. So with the stack, we think about it as a restricted container. When we put something in, we have to put it to the left of everything we've already put in. Because we're pulling from the left, and the next thing we put in has to come out before everything that's already in there when we put it in. Okay, well, if you start doing that, what you see is that you can never have an increase. You can never have a 1, 2 in the container, because that would mean you put something later after something before. So, we have to avoid 1, 2. In a stack, our container has to avoid 1, 2. And that means the permutation has to look like a single decrease in there, in the container. Okay, and if you think about it, we're just pushing in and we're popping off. And really, there's no reason to have a bypass in this situation. Okay, and then what about two queues in parallel? Let's think about it in the same restricted container setting. In the two queues in parallel, well, what we said is that we could just put our two increasing sequences into the queues and then figure out how we're going to pop them off the queues. Okay, so think about filling both the queues. Now, think about the stuff in the bottom of the queue we'll just keep in the restricted container. The stuff in the top queue, we'll output it as we need by bypassing the container. Okay. So we can mimic two queues in parallel if we make this thing be an increasing sequence. So that would be not containing 2, 1. Okay, and then what we're going to do is we're just going to fill the queue with one increasing sequence. As we see the elements of the other, we'll pop off from the container until we get to where it needs to go. We'll bypass with it. Oops. We'll bypass. Okay. So what we'd like first is a theorem that relates what the container is avoiding to what the permutations we generate are avoiding. So just a little bit of notation. We have okay. We're going to use this skew sum, it's usually called notation. In the pictorial perspective, what it looks like is the plot of pi above and to the left of the plot of sigma. Just add, or just, take pi, add the length of sigma to all its entries, and then put sigma after it. If you're thinking about it just a little bit. So here's our theorem. So the AVB machine generates the class I look to write AV1 minus B, which is really just mean prepend a new largest entry to all the things that your container was already avoiding. So let me give you a sense of the proof of this. This is really kind of a trivial proof. Okay. For one direction, we clearly can't generate any of these permutations 1 minus beta. So if the container is supposed to avoid beta, we're not going to be able to generate 1 minus beta. Okay? So this, remember, is beta with a new largest entry. So maybe I'll draw a picture of that. It's a new largest entry. And then we'll let beta is. If we try and generate this, in our input, maybe I'll do that over here. Well, our box, one of the things that it has to avoid is beta. All the things in beta come before this new largest entry because they're smaller. Okay? So by the time we read whatever this largest entry is, which is over here, we've got to have a copy of beta sitting down here, and we're not allowed to. Okay? So we clearly can't generate that. In the other direction, let me take some permutation that does avoid this. And I'll tell you exactly how to generate it with the AV beta machine. Okay. First, list its left to right maxima. So these are the entries that are larger than everything to their left. There's no entries up there. Okay. Now, as these entries come in the input, we get them from smallest to largest. So by the time, and we're not going to be allowed to output anything until we output the first left to right maximum. Okay. But we look down here and we see these entries that are smaller than it have to avoid everything in B. Because the whole permutation avoids 1 minus b. Okay, so we're going to, as we read these input entries, we're going to be able to put them in the right order in the container. Okay? So they're in the right order in the container, just like this. We come to this entry in the input and we bypass the container. Then the container will look exactly like this little subpermutation. We output that part. Okay? And now we keep reading. As we read, we're reading this way from the input. We get this little slice. Everything here now has to avoid B. So we're allowed to get this part in the container. We come to read this entry. We bypass the container with it. And then we output everything here. And we just keep doing that, working up, bypassing, outputting, up, bypass. So this is not a deep theorem, but it tells you immediately that the stack generates the 3, 1, 2 avoiders, and that 2 Qs generates the 3, 2, 1.
It's not deep, but it's beautiful.
Thank you. And in fact, it answers a bunch of other questions. So, well, not a bunch maybe, but we can look at a class. We can look at how a class is defined in terms of pattern avoidance and see immediately if it comes from a C machine, and if it does come from a C machine, which. So there's this class that Bona enumerated. One, 3, 4, 2. It has an algebraic generating function. I mean, he got it with a bijection to beta 0, 1 trees or something. And then the same enumeration, so the same enumeration for this class, which is not defined in terms of sorting, came up in work that I believe it was Albert Atkinson and Murphy and Brewstridge, or some subset of them, had done on sorting. They came up with the exact same generating function for a different looking class. And so Bona asked, well, is there a sorting machine that sorts this class? Okay, because they're equinumerous to something that's sortable. Well, maybe not this class, but if I just flip this avoidance upside down, this is, I just flip all these permutations upside down. Instead of avoiding this, they avoid 4, 2, 1, 3. This is the permutation sortable with the AV Sumatra machine. So immediately we know there is, yes, we can get those with the sorting mechanism. And it's all because of this 4. Okay. Other questions?
It doesn't make the enumeration any easier, this fact.
We've never tried, but it seems like it wouldn't be much easier to go this way. That's right. Okay. So speaking of enumeration, we'd like to use these machines to count these classes. Use these machines to count. We want to enumerate the class the machine generates. So we need rules that guarantee that we're only going to generate each permutation once. So I'm going to make rules on the sorting operations to ensure we can only generate everything once.